Week will be looking at the contents of week 11, which is towards understanding the practical applications such as measurements of different kinematic systems, measurements of different movements uh, or body segments, movements a body segment undergoes. So, measurements in a 3D space is usually done in two forms, either as linear kinematics, wherein the displacement, velocity, and acceleration are linear vectors, or angular kinematics, wherein we compute the angular displacement, angular velocity, and angular acceleration. Now, coming to the methods that are used to measure the orientation in 3D space, there are four major methods. Optical trackers, which are essentially stick markers that are placed throughout the object, and then the motion is tracked. These optical trackers come in two forms, either as passive marker systems or as active marker system. Passive marker systems are usually have a reflective coating, so when bright light is shined on them, there is a reflection, and this is what the cameras capture. Active marker system uh, produce a wave produce and a light of their own, of a particular wavelength, and the sensors or the cameras track the production of this light, and that's how the motion is tracked. There is one more method wherein which is essentially a glove which has sensors for bend sensors. So if there is bend, there is a change in the resistance, and this is sensed by the glove, and then the information is relayed. This is usually for hand and finger kinematics. There is also electromagnetic tracking sensors, which leads to production of electromagnetic force upon movement, and is uh, this is slightly more accurate than a hand data gloves. Uh, the fourth method is a inertial measurement unit based hand kinematic measurement system, wherein there are different sensors throughout the arm, and this leads to and motion within the hand leads to some information getting relayed to the system. Okay. To understand rotations, to compute different parameters from the rotations, there are three major uh, terms: rotation matrices, quaternions, and Euler angles. This lead to ease of visualization. What is the range of motion if there is a discontinuity in motion? Uh, there is there is one more thing, that if so essentially when there is movement, uh, when the movement is getting tracked, there are sensors placed on, say, the forearm, or on the upper forearm and the lower upper arm, or or and the forearm. So these sensors are usually placed on the skin. There is a difference between the bone and where the sensor is placed, which is a lot of soft tissue usually. If there are any artifacts arising because of this, is a very big problem, a very well debated problem, and the field is known as soft tissue artifact field, wherein whether the difference between the distance from the forearm to the skin leads to any artifacts in the measurements. Okay. So, three different parameters: rotation matrices, water ions, and Euler angles. Coming to rotation matrices, which uh, which is essentially the rotation of, if the axis, if the xyz axis were to rotate with the object without changing their relative angle, without changing the angle between the object and the axis, the rotation that is resultant from that is called as a rotation matrix. When there is no rotation, then the Cartesian system can be represented by this 100, 010, 001 x, showing the x, y, and z coordinates. However, suppose there is an object P which uh, there is an object at P which is at a distance of r from the origin and at an angle theta naught. If this particular object rotates and goes to the position P dash, which is at an angle theta, and since it's rotating and not translating, the distance remains same as r. So in that kind of a condition, you will, how will you know what P dash is? This is say Px, Py, and P dash is Px dash and Py dash. So Px can be written as r cos theta, Py can be written as r sin theta, and you can write cos theta as Px by r, sin theta as Py by r. You can write Px dash as r cos theta not plus theta, and Py dash as r sin theta not plus theta. So if you were to write Px dash, it will be r cos theta naught plus theta, which can be expanded to as this. Py dash will be r sin theta naught plus theta, which can be expanded as this. You got Px P cos theta as Px by r from this, and sin theta naught by as Py by r from this. If you substitute that into these two equations, you get Px dash as Px cos theta naught and minus Py sin theta naught, and Py dash as Px sin theta naught plus Py cos theta. This particular thing can be represented in form of matrix, wherein Px dash and Py dash are the final coordinates and Px and Py are the initial coordinates. The rest can be represented as a matrix, which is known as a rotation matrix. So essentially Px and the rotation of the object rotates the object from a point P to P dash, and this the angles of the rotation leads to a rotation matrix like this. Now this is in 2D. What happens in 3D? In 3D, there since there are three axes, if the rotations if there is an angle, the rotation angle is theta, and the rotation is along x-axis, your rotation angle looks like this. Whereas if it's along y-axis, your rotation angle looks like this. Along z-axis, the rotation angle looks like this. Note that if it's along x-axis, these terms, apart from the unity, these two every other term is 0. And it's similar for the other um, axis. If theta is equal to 60 degrees and the rotation happens along x-axis, you can apply theta is equal to 60 degree into this and you get a matrix like this. This is essentially the rotation matrix. Okay. So it is some of the properties of rotation matrix is that the columns of rotation matrices are unit vectors. The columns of rotation matrices are orthogonal to each other. The inner product of any columns of the rotation matrix is 0. Rotation matrices are commutative. Inverse of a rotation matrix is its transpose. Okay. So rotation matrices are commutative essentially means A cross B is not equal to B cross A. And inverse of a rotation matrix is its transform. A inverse is equal to transpose of A. Okay. If there were a square which was rotated at an angle of 60 degree along the, so this is x and y axis, if it were so whatever rotations happen along this plane will happen about the z axis. Okay, so uh, just a second. So to compute the final points after the rotation, you can multiply the rotation matrix since the rotation is happening along the z axis. You would use this formula. Multiply the rotation matrix into the matrix that is formed by all of the points. This is P1, this is P2, P3 and P4. So to multiply it, you to get the first term, to get this term, you multiply this particular line with the column here. We multiply one of the rows to one of the columns to get this term. And similarly, multiplying this with this gives this. Whereas multiplying this with this gives 0. And that's how you would compute. You can use a calculator and compute the rotation. And therefore you get the final points P1 dash, P2 dash, P3 dash and P4 dash. Now coming to, now that you know what rotation matrices are, how would you animate it? To track, so it's not always that an object move for 60 degrees and then it's not always that an object moves for 60 degrees and then uh, just stops. It's a gradual thing. So to uh, measure, to represent that, what you so this has a 60-degree angle with an increment. This essentially means there is a 60-degree angle with increments of 1 degrees. So you have, so the rotation, this is the x-axis, so the rotation, and this is the yz plane. So the rotations are happening along the yz plane but in about the x-axis. So your rotation matrix will be Rx, if you remember that. Your initial coordinate matrix will be this. So as your theta changes, your uh, the final matrix that you get will change. To represent that, you can use a quiver 3 function in MATLAB, and you can compute the uh, so it computes one matrix for each of the theta and then plots it. The code will look something like this. This is the initial xyz point, and the angle of rotation is 60 degrees. The you define the rotation matrices, and then you, to find the rotation, if the rotation is along z instead of xy, you multiply the rotation matrix along about z with the xyz, and you add the quiver function so that it loops as the theta changes every time. If your rotation was to be about y axis, then you would use ry. If it's along x axis, about x axis, you will use rx. Okay. Okay. In this case, the rotation is about x axis, so rx. In this case, the rotation is about y axis, so ry. In this case, the rotation is about z axis, so rz. Okay. And these are more animations where these are these are at some distance from the frame and are rotating with the frame. This is the rotation angle, whereas these are present, the object is present at the origin of the frame. Okay. Coming to uh, if you were to write a pseudocode for rotating any object defined with respect to the rotating frame, so fill 3 lets you uh, produce an object and filled object in 3D, and then you let the code know of all the coordinates, and then it will create a surface. For example, if you were to consider the surface S1, which is P1, P2, P3 and P4 are the vertices. Uh, so, uh, so, so this will be P1X, P1Y, P1Z, P2X, P2Y, P2Z. So you can use the command filter to produce an filled object, and then you give it the details of the object. In this case, each of the surfaces have these type of coordinates. So you have one surface S1 here, one surface S2 here, maybe S3, S4. So six different surfaces. So the code will be written likewise. Now if this was to be rotated at some angle theta, to know the new rotated points, you along, if rotated at about x for some angle theta and theta changes continuously, then you multiply the rotation matrix with the original points, and as the theta changes, this multiplication changes, and then you can produce a new solid figure using fill 3 command again. Okay, now, so up until now, whatever rotations we looked at, in those the angles of rotation for each of the axes was the same. All of them rotate at an angle theta. However, this might not be always the case. Most often than not, the rotation of along each of the about each of the axes will have a different angle. Suppose the rotation is such that about x the rotation is psi, about y the rotation is theta, and about z the rotation is phi. Then, since it's about z, for phi you write the rz, for theta you write the ry, and for psi you write the rx. You multiply these three matrices and you get something known as a composite rotation matrix. Furthermore, the here we are assuming the rotation is along first along x, then y, then z. It might be the other way around. And the sequence matters not in rotation matrix but in Euler angles. We'll come to that. So, if to compute the Euler angles, first of all, you can know the theta. If you know the values of this particular matrix, you can, if say this particular matrix was 1 1 0 2 3 1 4 minus 2 0, random numbers that might not mean anything, but if this was the case, then you will do, this was the case, you would you essentially know that the sine theta will be this term. Okay, so you know the value, you can compute theta as sine inverse of this particular value. Similarly, you can either compute phi, since you now know theta, you know cos theta. Either you can compute phi by doing a sine inverse of R23 term, or by cos theta, or cos inverse of R33 term by cos theta. Or you can divide these two terms R32 by R33, which gives us tan of phi, and then you can take an inverse of this and it will give you the value of tan inverse of this and it will give you the value of phi. And similarly you can compute tan psi by dividing these two terms, and you can compute phi by taking a tan inverse. To compute the Euler angles, you use something known as the direction cosine matrix and the rotation matrix and the sequence at which the rotations happen. If they happen first along y, then x, then z, first along x, then y, then z. You need to know that. So it can be xyz, it can be xzy, it can be yzxz, can be yzx, it can be zxy, or it can be zyx. Okay. Suppose one of the problems that occurs while using Euler angles is known as gimbal law. Suppose theta is pi by 2, which essentially means two of the axes have aligned. Theta is 90 degree. Then in that condition, if you solve this whole matrix, you get something like this, which simplifies into phi minus psi. So whatever degrees of freedom you had earlier depended on three angles. Now it depends on only one of the terms. So the degrees of freedom decrease. So this is one. So essentially the system becomes slightly redundant. So this is one of the problems that happens while using Euler angles. So one needs to be careful while using this. Now, suppose there is an arm which is the forearm has rotated with an angle 60 degree. The upper arm has rotated at an angle 20 degree. To calculate the sum of these two, so these are simple angles 20 and 60 and we know the angle, so it's fine. To compute the sum of these two angles, you can multiply the rotation angle R1 with the rotation matrix R1 with the rotation matrix R2. Now these, if you look at the coordinate system here, these rotations happen about the y-axis. So you write the ry theta matrix. In first case theta is 20 degrees, in the second case theta is 60 degrees. Okay, so if you were to multiply these two rotation matrices, you will get something. And if so this if this, which is a new rotation matrix which tells you about the sum of both of these rotations, if you were to compare it with the ry theta matrix, you can see that theta is either cos inverse of this term or sine inverse of this term. So if you use a calculator and calculate this, you will get theta is 80 degrees, which is the sum of these two. If you were to take a transpose of R1 and multiply it with R2, you will get something like, you'll get this. If you compare this with this, you can either write theta as a cos inverse of this term or sine inverse of this term. So theta becomes 40 degrees. This theta is tells us about the net rotation, which is a difference between these two angles, this angle and this angle. Couple of more things to note is that, firstly, every 3D rotation corresponds to rotation by an angle about an axis. If the rotation is about one axis, then it's a 1D rotation. If there it's about two axis, 2D, and if about three axis, it's a complete 3D rotation. But each of the axes will have an angle to it. To obtain the net angle of rotation, if you have a rotation matrix such as this, and you calculate the trace of the matrix, the trace is essentially the diagonal elements, the sum of the diagonal elements. This is the formula for trace. Okay, so 1 plus 2 cos theta is equal to the trace of r. Now you won't know cos theta, the theta, so you can calculate the theta. If these were random numbers, you can calculate cos theta is equal to trace r minus 1 by 2. So theta is equal to cos inverse of trace r minus 1 by 2. Coming back to some of the basics, so any complex number is of the form a plus ib, where a is the real portion and b is the imaginary portion. If you were to represent a plus ib in a Cartesian plane where one of the axes is real and one other one is imaginary, this line will be a vector. The angle that the vector makes with the real axis will be this by this. This is b, this is a. So theta will be tan inverse of b by a. The magnitude or the length of this particular line will be, so this is tan inverse of imaginary by real. Okay, the magnitude of the of the length of this line will be root over of a square plus b square. Now if you were to represent complex numbers in a 2D plane, this is how it will look like. So if there is an object here at with the coordinate c plus id and an object here with the coordinate a plus ib, the positional information is such that the length of a square plus b square and c square plus d square is equal to 1. For any complex number to represent rotation, the length should always be equal to 1. So this length is 1. You know A and you know B, you know C and you know D, you know the angles that these form with the real axis. To compute the the sum of these two rotations, what you can do is you multiply A plus IB with C plus ID, which will give you another imaginary number. You can compute theta by using tan inverse of imaginary by real, and you get theta as 75 degrees, which is essentially 45 degrees plus 30 degrees. It's interesting to note that the length of this is again 1. If you want to know the relative orientation, you can use a conjugate instead. The conjugate of x plus iy is x minus yy. So if you remember in the previous matrices, we took the transpose of the first matrix and multiplied with the second matrix, which let us know the net angle. To calculate the net angle here, you take a conjugate of c plus id, which is c minus id, this entire term becomes c minus id. Okay, so you multiply this, you get another imaginary number. The length of this number is also equal to 1 because all of these lie on that circle. Tan inverse of imaginary by real gives you 15 degrees. So, if you were to compute a plus ib into c plus id, you get something similar to an addition of angles. Whereas if you take a conjugate of c plus id and multiply it with a plus ib, you get something similar to subtraction of angles. So this will give you the relative orientation. To represent 3D rotations in using quaternions. So quaternions are essentially in a 4D hypersphere, wherein A, B, C, D belongs to a 4D hypersphere of unit length. So A square plus B square plus C square plus D square is equal to 1. So any point on the surface of this hypersphere will always be at a distance of 1 from the center, and this can be represented in this form. So initially this is the real portion and these are all the imaginary. This is real and these are all the imaginary portions. This was your 2D complex number, this was a 3D complex number, and this is the final 4D hypersphere complex number. To represent rotations using quaternions, you represent the angles of rotation, axles, and the angles of rotation. To represent that, suppose you have a coordinate of this kind: cos theta by 2, vx sin theta by 2, vy sin theta by 2, vz sin theta by 2. So Vx, Vy and Vz represents the axis about which the rotation of theta has occurred. If Vx is 0 and Vy is 0, then the rotation has occurred along Vz about the z axis. If Vy and Vz are 0, the rotation has occurred about x axis. So if you look at this one, 0, 0, 1, 0, then cos theta by 2 is equal to 0, theta by 2 is equal to cos inverse of 0, so theta comes up to be pi. And since these two terms are 0, the rotation has occurred about the y-axis. Again, 0.70700, 0.707. In this case, cos theta by 2 is equal to 0.707. So theta is equal to 2 cos inverse of 0.707. This term is 45 degrees. So theta is equal to 90 degrees. And since these two terms are 0, the rotation has occurred about the z-axis. If there is some random number 0, 1, 1, 1 and 1, then suppose the number is 0, 1, 1, 1, then the net rotation is pi, which has happened along x, y and z, 3 directions. Okay. Now, the quaternion can be converted into other forms of parameterization. It can be converted into Euler angles using this particular formula. To use it within the code, for this case also you need the sequence of the rotation, whether x within x, y and z, if it was x, y and z, or if it was x, z, y, etc. So okay, if you have these terms, you can compute the Euler angles, then input it you can compute the Euler angles by inputting all of these information into MATLAB, and it will give you an idea of what the Euler angles looks like. Coming back to the previous problem that we had, this can be represented if the rotation is about the y axis. If the quaternion will look something like this with these two terms as 0, whereas for this point the quaternion will look something like this, okay, with these 2.0. You using these two composite using these two complex number, you might multiply the absolute the complex numbers, and you get the sum of both of these angles, or you can multiply the conjugate of q1 with q2, and you get the difference between these two angles. Okay. Sorry, there was a network issue. I'll just reshare the screen. Okay. So, where was I? Huh. So, if you are to multiply two of the points in the imaginary system, you will get some the theta similar to adding both the angles. Whereas if you are taking a conjugate of one, multiplying it with the other, it will be similar. The angle that will get, it will be similar to subtraction. Okay. Now coming to quaternions, which are in a 4D hypersphere. So they have, instead of x, y, z, they have, say, another parameter, another coordinate k also. So they instead of a 3D space, they belong to a 4D hypersphere, and the sum of all the squares of each of the numbers is equal to 1. This will be your complex 2D number. This is your complex 3D number. However, for a quaternion, since it's in 4D, there is one real part and three imaginary parts. Okay. Okay. So, to represent your any rotation through quaternions, you can follow this formula, wherein uh, the if theta is the angle of rotation, uh, Vx, Vy, and Vz represent the axis about which rotation has occurred. In this kind of and you can represent your rotation and all of the axis using this particular coordinate. Suppose your suppose you have a quaternion 1 0 0 0, then the cos theta by 2 component is equal to 1. Theta by 2 is cos inverse of 1. So, uh, cos inverse of 1 is 0 degrees. So, theta is equal to 0 degrees. And since sine theta by 2 is supposed to be equal to 1, sine 0 is 1. So, you get V1, V2, V3 is equal to 0. This is also solved. Let's try to solve this. Again, cos theta by 2 is equal to 0. So, theta by 2 is cos inverse of 0, which is this cos inverse of 0 is pi by 2. So, theta is equal to pi. And your so this essentially means that your theta is uh, 180 degrees and your rotation is happening along y-axis. Coming to this one, cos theta by 2 is 0.707. Theta is equal to 2 times cos inverse of 0.707. And so this is 45 degrees. So theta is 90 degrees or pi by 2. And whatever rotation is happening in, so the angle of rotation is 45 degrees along the z-axis. So quaternions essentially let you represent the angle, axis angle, and which is the axis that the rotation is happening about. If you want to convert the quaternion to other formats, you can convert it to the Euler. This is the rotation matrix. You can convert it to the Euler angles using this particular code in MATLAB, and you can convert it into and you can use this matrix to convert it into a matrix form. To represent how what kind of angles are there, you can, similar to what we did here, you can take a conjugate and then multiply, which will give you the difference between both the angles, the relative orientation of sorts. Or you can multiply both the numbers as it is to get a sum of both of the angles, which is what they're doing here. If the angle is 20 degrees and 60 degrees, and you can, since everything is in xz, so everything is in xz plane. So you have the x component, you have the j component, but you don't have I or k components, other two imaginary components. You compute your quaternion and you get the sum of both of these angles as 80 degrees and the difference as 40 degrees. One more thing is that order of multiplication matters if you're working with matrices. If you want to multiply these three matrices, multiplying these two first and then with this leads to a different results than multiplying these two first and then this matrix. Okay, now let's solve some problems. Just let me share a different file. Coming to the first whole assignment question, which of the following are true for rotation matrices? The columns are orthogonal vectors, the columns are unit vectors. It follows commutative property. Inverse of rotation matrix is its transpose. The answers is A, B, and D. It does not follow commutative property. A cross B is not equal to B cross A. Devices used for measuring orientation in 3D space include optical trackers, gyroscopes, electromagnetic tracking sensors, inertial measurement units. Except for gyroscope, all of the other three are answers. One more option was the flex sensor hand glove. What does a quaternion consist of? Two real parts, two imaginary parts, a single real part and three imaginary parts, four real parts, four imaginary parts. The answer is a single real part and three imaginary parts. Remember, A plus IB plus JC plus KD. Gimbal lock occurs when two axes of rotation align. Rotation axis 180 degrees. The rotation matrix becomes singular. The trace of a rotation matrix equals 0. The answer is two axes of rotation align. Please stop me if there are any questions. The columns of rotation matrices are orthogonal to each other. True. Rotation matrices are commutative. False. They are not commutative. Quaternions extend complex numbers to represent 3D rotations. True. The measurement of orientation in 3D space includes kinetics, linear kinematics, angular kinematics, fluid dynamics. The answer is linear and angular kinematics. Which of the following cannot be used for hand kinematics measurements? Flex sensor based detector gloves, optical trackers, electromagnetic tracking sensor, and force sensors. The answer is force sensors. These are used for kinetics measurements, not kinematics measurements. Match the following. So essentially, Euler angles are defined by three rotations about the principal axis. Quaternions involves a 4D hyperspace for representation. Okay. And rotation matrix uses orthogonal unit vectors for representation. The answer is D, not C. There was a mistake here. Which MATLAB function is used to create a filled 3D surface based on provided coordinates? Plot 3, mesh grid, fill 3, and surf. This was present on one of the slides where the code produced a cuboid of sorts, and the answer is fill 3. If Vx, Vy, Vz represents the axis about which rotation theta has occurred, the quaternion representation is given by cos theta. The answer is supposed to be cos theta by 2, Vx sin theta by 2, Vy sin theta by 2, and Vz sin theta by 2. So A. For a counterclockwise rotation of 20 degrees about y-axis, the correct uh, rotation matrix is, so since the rotation is in y-axis, first option and the last option are anyway invalid because these are rotation matrices along x-axis. So you have two more options. Remember the matrix was cos theta minus sin theta, cos theta, sin theta minus sin theta, and cos theta, apart from the middle portions. So this is essentially cos 20. This should be cos 20, sin 20 minus sin 20, and cos 20. Cos 20 degrees is 0.9397 using a calculator, and sine 20 degrees is 0.324. So the answer is B. The quaternion denoted by Q 0.70700 represents a rotation of dash degree about dash axis. So since this is something that we solved in the during the recap, so this term the first 0.707 is the cos theta by 2 term, and so the theta comes up to 90 degrees essentially, and the rotation has happened along z-axis because there is a term here where there is no terms here. So the answer is 90 degrees about z-axis. Singularity is a major problem usually incurred while using Euler angles, quaternions, rotation matrices, or none of the above. The answer is Euler angles because if the two axes overlap, then the degrees of freedom go down. That's it. Please let me know if there are any questions. If not, that's the end of the class.